Welcome back to Matrixology. So we are going to work on solving systems of linear equations. We're going to lay out a very formal way of doing it, and it's called elimination, because in math people like to come up with pretty intense words. Maybe they weren't picked for soccer when they were kids, but anyway, so that's what we're doing, elimination. All right. So you can imagine this all being said in Arnold Schwarzenegger's voice. So, whatever you like. Let's see. So I've got a few things written down already. So we're going to solve these equations. It's how we can do it and how computers will do it, in fact, right? So we'll be ultimately learning about how computers will do these things efficiently. We can do it for little ones, right? With pencil and paper. So that's the plan. So we're going to use elimination. We're going to use row operations to perform elimination. So that's a big thing here, right? So we're going to go through the anatomy of what that means. But it is basically, adding equations to each other with multiples. We're going to do it, which you may well have done with so-called simultaneous equations. It's exactly the same idea. It's exactly the same plan, but we're going to have a very structured way of doing it. So anatomy of row operations, that's going to come, right? So that's this piece. There's a big story here about triangles, right? So this is ax equals b, but, and that's usually a rectangle times a vector equals a vector. We're trying to get to some kind of triangle story. So we'll get to that. But basically it'll be rectangle equals triangle times triangle. Cool, right? So that's a thing to look forward to. I'm sure you're thrilled. So back substitution, yes. Okay, so that is part of the game. So we do row operations and then back substitution. Just get the right words in here. So there are a couple of things we're going to learn about that are part of matrices. Pivots, right? They're really essential objects. Elements of each matrix has a selection of these things, and we'll explain what they are. Multipliers, big deal. It's a bit sneaky. This is a small l, right? This is a curly l, E-double-L, with subscripts ij, and that's the entry that will be an entry in a matrix, which will be a lower triangular matrix. We're going to get to that, but it's L for a reason because of lower. Upper triangular matrix, U for upper, right? So a little bit of a spoiler there, right? So but that's good. So these L's have a plan. It's going to be slowly uncovered what it'll take a little while. And then augmented matrix, very nice thing. So numbers in boxes, clean and tidy, none of this kind of calculus stuff where things are kind of messy or very tidy. I seem to have fallen over. And kneeling, back issues. So let's see. So, and then when things go wrong, like how do you do it? So they don't really go wrong. It's not wrong. But this is the zero solutions or infinitely many solutions case that we've talked about. So we're going to work through a 2x2 example, then a 3x3 example, and we'll come back to a couple of 2x2 examples that show you when things go wrong. So, all right, so off we go. So here's our equations just set up. So I'll just write it straight down and we'll get on with it. And I'll show you how, as we do these row operations, the system changes. So that's very key. System will change, the solution won't. So we want to get to a simple system that has the same solution as our complicated one, right? And that will make us very happy. I mean, probably can't get much happier than you are right now. So, but I can tell you it's possible. So simple one, it's x2, so it's a 2x2 equals 1. This is our first equation. I'll label it in that old way. 2x1, we'll start to call that row 1. That will be the way to do it. So plus x2, this is a very simple one. Was 5. All right. So it's a 2x2 system. And again, this is always the case that this is m equals 2 equals number of equations. Good to write it out again, badly. And 2. This is a number of variables. All right. There's x1 and x2. We'll get to rectangular kinds of things later on, but to start with, it's squares, all right? Keep it very tidy. So the way we'll do this, we'll actually change this. We're going to call this row 1 and row 2. Right, so these are now row 1. So it's R with a sub 1, right? Just an R. R sub 2. I want to say that every time I write a vector, I will put a little arrow thing on top. And every time it's a matrix, it will have this kind of blackboard structure, right? So I've written out other places, I guess, but I'm just going to say this. So B, C, Z's are always fun. Okay, good. So you know what they are. I advise using that approach or something that makes it very clear. You know, it's hard to change the font for yourself, so you have to do a good job, right? Yes, Comic Sans for equations. Okay, I apologize. All right, so let's imagine this is row 1 and row 2. So let's change row 2. We're going to have a new row 2, and the way to do this, so this whole system, right, is going to move into a new system, and we won't change the first row. 3x2 equals 1. That's just, this is row 1 still, unchanged, right? But row 2 we're going to change, and I'll do it like this. I'll say row 2 prime. You know, let's make a different color. This is a big deal. So row 2 prime, the new row 2 is the old row 2. We always do this. Always do this. Minus, right? Always do this. Some structure here times row 1. Right, so this is the anatomy that I was talking about. We always use this form. Don't, I mean, yes, you can do it faster. I mean, there's lots of obvious things where you say, oh, you know, I can just do this and this. Don't do it. Don't do it. Don't do it. Because we're trying to build up to 60 billion times 30 billion, right? We're trying to build up to this thing. So we're going to have a real structure. We have to tell computers. They get confused. Again, they'll win eventually, but at this point, they get kind of confused about these things. So there's always, and there's a fraction in here. So this, everything here is structured. And so we're trying to get rid of this. So the game is, so this is a eliminate here. And really we're trying to get rid of this whole term. And you can think of it as we're trying to get rid of that 2, right? So if we added 2 of the first row to the second row, it would work, right? So yeah, 2 of that first row, we get rid of it. A way to do this formally, right? So we've got this minus sign here. So we're going to subtract, we're always going to subtract rows from each other. That's how you subtract, you go like this, subtract, okay? Apparently. So let me put in red what these things are. So this will be 2, right, divided by minus 1. So what are those guys? So these are, let's use a different color. So this minus 1 is this minus 1 here. That's a minus 1. And this 2 is this 2. So that's always going to work. Whatever's that, if this was a 7 and this was a 14, right? If we had a 7 here and a plus 14 here, we do 14 divided by 7. Right, this minus 1 on the bottom cleans up that minus 1 on the x1. We multiply by 2, and now it's the same thing. We have a 2x1. And then we subtract it, right? So we subtract it. We subtract it. Okay, so do this a bunch of times and you will believe, hopefully. So this whole thing in here is really a plus 2. Fine. But the minus is very important. And we're going to give this is a special thing. So we're going to call this thing in here L21. Right? So the 2 is the row that's being affected. The 1 is the row that we're using to do the work. So this is now, I'll do this. It's now 0x1, right? We're really adding 2 of the first row. And if we add this one, so that's a different color, we're going to add 2 times the first row, so that we get a 6x2 up here, right? So there's a 6x2, we're going to add it to this guy. And we get plus 7x2. Add 2 of this one to 2 of this 5, or to just 5, and we get 7, suspiciously. Right, so this is row 2 prime. So this guy is gone. right? That was the plan. And now row 2 is very simple, the new row 2. And now we drop the prime, we say this is just row 2. So we've changed our system. It's a different system, right? So the second equation is now x2 equals 1, row 2. So we drop primes. Just in that little equation where we say row 7 prime is row 7 minus whatever, we do drop primes. So it's now just x2 equals 1. That's very easy, right? That's very easy. So we've changed, let's look at the original system. It's simple enough, we can draw it. So the original system was this. It's going to be two things. There's an x1, x2, there's a 5 up here. This is 2 1/2. And I think this is 2, 1. Okay, so that's something, I think this is about right. Yep. And there's a -1. That's a 2, that's a -1. It's not really true, is it? But anyway. Okay, there are two equations. So this is our original equation 2. So let me write it out. This is 2x1 plus x2 equals 5. And this is minus x1 plus 3x2 equals 1. Minimal lying. Right, so these guys hit at a point here. We haven't quite finished the solution. I'll get to it. This is the original, right? So this is the original. So now our equations are different, right? So this is row 1, this is row 2. Now our equations are a bit simpler. So in fact, we still have the first one, right, going through 5 and 2 1/2. So we still have this one. This is our I've lied completely. That one's gone. Yep, that one's gone. This one is still here. Let's get that right. So this is minus x1 plus 3x2 equals 1. And then we have this nice thing that I've told you what the solution is, I guess, 2 and 1. So this is x2 equals 1, right? So it's one of these equations. You have to think about it maybe a little bit. This is, excuse me, so this is x2 equals 1. So this was a row 1, this is row 2 prime, right? So it's the new version of row 2. So it's the same solution, but different system. But a simpler system, right? I mean, flat line like that is very simple to work with. Okay, so that's a little piece, maybe come back to that in a second. We've got x2 equals 1. Right, so we have, okay, we've sort of jumped a little bit there. We have x2 equals 1. Right, so now solve for x1 using back substitution. So this is this thing that we would do. You only need to do it once for a 2 by 2, but you do it much more for a 3 by 3. So back substitution. So we go back and substitute it into equation 1. Right, so equation 1, which is still healthy. So minus x1 plus 3x2 equals 1. So we put into here x2 equals 1. Okay, boom. And that gives us minus x1 plus 3 equals 1. We unwrap this and we'll get x1 equals 2, right? So we get a minus 2 and then take away the minus sign. So this is x1, x2. This is our solution, is in fact 2, 1. So this is our solution. So we're done. Right? Done. Easy. Okay, so there are two steps. There's elimination and then back substitution. And I'll recapitulate that. Again, 3 by 3 example is important to see a little more complexity, right? Usually the case, we can open the door with 2 by 2s, 3 by 3s, we need to think a little bit more about things. We can actually go further, and I think that's an important thing to state. So, for this is somewhat for later, but it's good to see what it does. we can go further, right? And really avoid and kind of avoid back substitution. But we could just keep working with the equations to make them simpler. And this is Gauss-Jordan elimination, where you get a little carried away and you eliminate all the numbers you can. So we were here. At this point, we were here, minus x1 plus 3x2 equals 1. And then we got to 7x1 equals 7, so I'm going to change it. 7x2 equals 7, so I'm going to change it to this, right? So this is, we'll just call these row 1 and row 2 at this point. Again, dropping the primes. So we could get rid of this character here. We've got this nice x2 here. The very important thing to see here is this is a 0 here, so there's no complication, right? We're not going to mess things up. So we can use this one to get rid of this x2, so I'll leave that there. So it's the same kind of notation, right? We're going to say, let's keep the second equation equals 1. So if you like, you can say row 2 prime equals row 2, unchanged. Row 1 prime, so this is our system. This becomes, we'll have a better notation for this as well. So this is the same thing. So let me write it out in that way with the formalism, right? So it's going to be row 2 prime, always like this, equals row 2, sorry, we're changing row 1 prime. Row 1, so row 1 prime equals row 1 minus some multiple, in this case of row 2. Everything looks the same. These we won't call L's, so this is not an L because we're going a little further. But it's got the same approach, right? So I'll put in red, so this is a 3 divided by a 1. And so the 1 is sneaking around here. Let me put it here, there's the 1, and I'll connect them. So this 1 is here, and this 3 goes here. Right, so it's 1, it doesn't matter. You could just see that you subtract 3, but this, you can hopefully start to see that this will always work for us. So we're going to subtract 3 of the second equation from the first equation. And that will give us minus x1, that's unchanged. We get the 0 here, plus 0, that's what we wanted. And we have 1 minus 3, so that's minus 2. So actually, this is the solution, right? We've done it. We'll get rid of the minus sign. x1 equals 2, and x2 equals 1. So what's this system? This system is very simple. And what we've done is we've taken lines that have slopes and started to remove them such that we still have a system with the same solution, right? So x2 is 1. This is x1. This is x2. Let me get this here. This is x2 equals 1. And this is x1 equals 2. And we have the same solution as we had before. Right, so this is 1, this is 2. Write that in black. This is 2, and this is 1. So we've had 3 systems now. We've had the original one over here. We have the modified one where we just did this one step of elimination, and then from there we were happy to do back substitution. And then there's this third one over here where we've gone Barney bananas with the elimination and ended up with a super simple system. So these systems are equivalent, they have the same solution. Very different, these lines are all different to each other, right? Okay, that is a good thing to know. All right. Okay, so let's just add a piece here. So the pivots have appeared. We didn't mention as they came through. The pivots are appear at the bottom of these multipliers, the L21, there'll be an L31, L32, these guys. So minus 1 in this case, right? But really, if you go back to the equation as you unwrap things, you see the pivots appearing. Again, we'll see this more strongly in the 3x3 example. But here's the first pivot here. It's really and -1. So this is, we're going to call it D1. We're calling it D. That's just what we're doing. Okay. There are other P's that we're sort of worried about. And before we divide through by anything, we get the pivots here. So this is the second pivot here. Now I did divide through later on, and that's going to complicate things here. This 1 on the bottom is not really this structure here. That's not the second pivot. So it's before you do any division. Okay, so we've done elimination. We've done one back substitution. We did further elimination, Gauss-Jordan elimination, that gives you the full solution. The reason we don't do that for normal systems or for large systems in practice is that computationally it's fine to just do this sort of first layer of elimination. And we uncover a beautiful structure that's true for matrices in general. So, okay, so we'll see more as we get into the 3x3. Just to recap, though, that there are these basic rules, and I need to add one more for you. The basic rules, elimination first and then back substitution. What we're trying to do is remove, we're trying to make an upper triangular system. Okay, again, we'll see this more in 3x3s and others. We're trying to get rid of this structure that's here, and it might keep going down. And then it's easy, then we can kind of march back up, right? So it was very easy to solve this problem, then you can substitute into here, solve this problem, and hopefully you can start to see that working back. It's possible, so these are row operations that got us to there, and then back substitution. It's possible we may need to do one more thing. Okay, so the basic rules, let me write them out. Elimination rules. And there's one thing that we'll have more examples for is that as we go through, and the second one is more subtle, is we create an upper triangular. So upper means that there's only stuff in the upper triangle. There are zeros, that's a thing, but there are zeros below some in a lower triangular part of the system. Create an upper triangular system by systematic elimination, right? Systematic elimination via row operations. Right? And these row operations always have that same form. And then 2, we may have to swap rows. And this is to do with these pivots. Swap rows if needed and if possible. If needed when pivots are missing. When pivots appear to be 0, equals 0, right? Because when we can't use them, right? You can't. Back in this form, which we're going to use over and over, this form, right? Very structured. New row is the old row minus some multiplier times some other row, and the pivot of the row that we're trying to change has to be on the bottom, that -1. If it's 0, then we can't do anything. So there are cases where it's 0 and we can fix things up. So an example of that would be just simply, so a very simple example would be x2 equals 3, x1, say 3x1 minus 7, x2 equals 0. There's no pivot here, right? There's a 0. I shouldn't say there's a 0 here, so we can't get rid of this. But we can just change this. We can say, and the way I'll start to use this sort of notation. Row 1, row 2, this big tilde thing. We're going to use that more and more. We'll just swap them. And so that's fine. Now we have a perfect upper triangular thing. All right, so I want to do this problem once more. So now we've got some basic rules there. So I just want to use the augmented matrix approach. So we've carried all these x1s and x2s around. We don't actually have to do that. Well, we can make it even tidier. but it's a little bit, tiny bit abstracted. Augmented matrix approach. Okay, so we had this original problem, and we don't have to do everything again, but I'll just show you the notation. And this is just to find the upper triangular structure. Plus x2 equals 5. This equals 1, this equals 5. So we transform this into the matrix problem. It's going to look like this. It's minus 1, 2, 3, 1. And all of this multiplies x1, x2. And this equals 1, 5. Right, so this is the row picture, which we know we can solve. This is the matrix picture. This is AX equals B. So as we do these row operations, let's think about this. It only affects each row. So this is a row. This is a row. The x1s and x2s don't get moved around. They should be x1, x2, x3, x4, right? They don't get moved around. So we can actually do all this in a very simple, tidy way by creating what's called the augmented matrix. So we just take minus 1, 3, 2, and 1, and we draw a line here. So it's just a line. And then 1 and 5. So this is the augmented matrix. This is really of the form A, and then a line, a bar, B. So from here, now we can do our row operations. And this is where we start to use kind of a nicer notation as well. So it's the same thing. We only have to do one row operation in this case. And I'm going to switch to doing it this way. Right? And we'll also move away from looking at how the equations move and so on. But that was very important to see how that changed. So same formalism. Let's write it like this. So row 2 prime is row 2 minus something times row 1. Right? And that will be, it's always this. Here's our pivot. This is D1. Minus 1 on the bottom. Right? This is pivot D1. Row 1, so those two things connect. And then 2 on the top. So let me use maybe a different color. This is the 2. This is the 2 over here. Right, so this guy is here. The pivot is on the bottom. So that's how we changed things. And now we've got a new augmented matrix. The first row doesn't change. We're just trying to affect the second row. Right, so we're adding 2 times the first row to the, and so we just take the whole row, multiplied by 2, essentially, that's what this is, add it to the second row. So minus 1 times 2 here, gets rid of this guy. This gives us a 7, this gives us a 7. All right, so let's write in this is the changed one. So 0, 7, 7. And now we're in this form. So we're done. We can't, in terms of making a triangle structure with zeros below what we'll call the diagonal, we can't do any more. And so we've uncovered, this is D1, first pivot, and this will be D2. So this tilde means is equivalent to. Let's put that in here too. So tilde means systems have same solution. Right, and from there we step out back to back substitution. You can see how the Gauss-Jordan thing would work very nicely too, because we could get rid of this 3, we could divide rows and so on. We'll come to that, that's very soon. We'll do that as well. But I think that is a good place to stop for this section. And then in the next piece, I'll show you a 3x3.